very much. Professor A.K. Chaturvedi, Professor H.K. Verma, Professor S.P. Nigam, Professor Narasimhan, my faculty colleagues, students, alumni, ladies and gentlemen. On behalf of the Department of Mechanical and Industrial Engineering, IIT Roorkee, I welcome you all to the inaugural lecture of Professor Shankarlal Memorial Lecture Series. The Department of Mechanical Engineering was established in 1946 and renamed in 1973 as the Department of Mechanical and Industrial Engineering, popularly abbreviated as MIED. We are the second largest department of IIT Roorkee with 42 dedicated faculties catering to more than 1100 UG, PG and research students. Though all engineering branches face tough competition with computer science, our department's opening JEE AIR is just below 2000. Our department lies in the bracket of 151 to 200 as per the QS ranking. We are a unique department of IIT Roorkee as we provide 2 UG programs and 5 PG programs. Apart from this, our department produces nearly 100 doctoral theses every year. Our faculty guide students for their PhD and master's dissertations and BTech projects and almost in all areas of mechanical production and industrial engineering. The number of publications in reputed journals by our faculty in the past academic year exceeds 350. Among them, more than 100 research articles are in the first quartile Q1 journals. In the last few years, department has completed hundreds of sponsored research and consultancy projects worth crores of rupees. Currently, we have a good number of sponsored research and consultancy projects in hand worth rupees 35 crore. Our faculty members and their team of students have filed multiple patents in the past year. Our faculty members have availed funding opportunities for schemes like Spark and UKRI. These schemes facilitates academic and research collaborations between Indian institutes and the best institutes or universities in the world. Let me take this opportunity also to introduce you with the bio sketch of Professor Shankarlal. Professor Shankarlal was born on June 24, 1923. He had an excellent academic career and did his bachelor's degree in aerodynamics from BHU Varanasi in 1944, postgraduate degree from London University, London in 1949, and obtained PhD degree from Caltech, USA in 1955. He joined Mechanical Engineering Department of the University of Roorkee as Associate Professor in 1959. He took over as Professor and Head of the Department of Mechanical Engineering for the years 1964 to 67 and 1970 to 78. Needless to mention that in his period only, the department has aided the industrial engineering and BTech in production and industrial engineering. He joined as Director IIT Kharagpur on 13 February 1978 for a 5-year term. After completing his tenure as Director IIT Kharagpur, he rejoined the Mechanical and Industrial Engineering Department on 13 February 1983. He was retired from the services of Roorkee University on June 24, 1983. He was elected as President of Institution of Engineers during 1982-83, Fellow of the National Academy Sciences India, Fellow of Royal Aeronautical Society London, and a Fellow of Institution of Mechanical Engineers London. He was the Vice President of Indian Society for Heat and Mass Transfer 1976 to 78 and President of the Indian Society of Theoretical and Applied Mechanics 1981-82. Professor Shankarlal had made meritorious contribution to the promotion of knowledge in the country. He was member of many major national committees which are responsible for framing science and engineering policies of the country like ACRC, UGC, CSIR, Railway Board and UP State Council of Science and Technology. He was well connected with the educational administration and was a member of Board of Governors of MNREC Allahabad and REC Srinagar. He passed away in USA on September 29, 1991. To know more about his academic and administrative capabilities, I request Professor S.P. Nigam, former head of MID and a PhD student of Professor Shankarlal, to share his reminiscences.
Thank you, Professor Gandhi. Professor Chaturvedi, Professor Verma, Professor Narasimhan, and Mr. Paul. I must thank Professor Gandhi for inviting me to be a panelist in this particular program. At the outset, was very happy when I got his invitation and an opportunity to talk about my student days when Professor Shankarlal was head of department. My first interaction with Professor Shankarlal was in December 1971 when I came to Roorkee for an interview for selection of PhD program under Quality Improvement Program of Government of India as a sponsored candidate from MP government. He was obviously heading the panel of the interview committee. I don't remember if Professor Verma was there or not at that time. And he was chairing that board. He had a vision even in 1971 to start a new area of noise. And he had a plan to start that particular area in the department. I could easily get selected because of my background of vibrations and noise for my MTech degree from IIT Kharagpur. And I was chosen as first QIP candidate in the department. After having joined the department, when I met Professor Shankarlal, he advised me to go to Dr. Grover because he was a man from vibrations area and noise was interrelated with that, and asked me to contact Professor Grover and get some problem in this particular area. I started working with Professor Grover, and after some time, he advised me to request Dr. Shankarlal also to be my co-guide. And when I requested, he readily accepted that. So he was my co-guide for my PhD program as well. During 3 years stay for the PhD program in the department, I had a couple of interactions with Dr. Shankarlal. And I remember one instance that sometimes in 1973, end of 73, beginning sometime at that time, finite element methods were finding its roots in Roorkee. And he advised me not to switch over to finite element method, but continue with the finite difference methodology for my work, for which I've already done. I put about more than a year that particular work. On his advice, I continued that way. So that's how I interacted with him during my PhD program. Coming to one of the unique feature of this panelist discussion, I'd like to point out that Professor Shankarlal was a linguist par excellence. He had a knowledge of 7 languages. Professor Verma will agree to that. He knew Spanish, French, Sanskrit, Punjabi, Bengali, and of course English and Hindi. And not knowledge, he was quite fluent and had a command in all these 7 languages. That was very unique and rare phenomenon, I must say that. Next point, which I call is his teaching abilities, capabilities. He was a very good teacher, loved by students. And he mostly took, if I remember during those 3 years, undergraduate classes, solid mechanics and theory of elasticity. And students never missed his classes. He was loved by the students, being a very good teacher. He had a good command on the subjects. And his fluency in oration in the classroom was very well received. As a matter of fact, if I remember correctly, he got Best Teacher Award a couple of times in University of Roorkee. And I was later told that even at USA, when he joined there as a professor, he was given this particular award of Best Teacher Award. So beyond this, what I feel is his magnanimity, his oratory skill, his debating skill, his administrative capabilities. All these bear a forefront in my mind. And he did work in research areas in the area of solid mechanics and elasticity mostly. And with this, I would like to pay my tributes to Shankarlal, and I have got fond remembrance of him. Thank you.
Thank you very much, Professor Nigam, for enlightening us with the memories of the Professor Shankarlal and also giving us some glimpses of his thoughts and vision. Also have Professor H.K. Verma, who is also former head of MID, and he is a colleague of Professor Shankarlal. And with his permission, I would like to play his one video which we shoot when he was honored here in IIT Roorkee, maybe the last year, sir. So I would like to play the video of Professor Verma with his permission, and then Professor Verma may comment on that also, that any additional things. So let me play the video of Professor Verma.
Yeah, Professor Shankarlal was a very renowned professor in mechanical engineering. He joined the Department of Mechanical Engineering in the year 1959. I was already a faculty member, young faculty member, and I had great guidance from him. He taught me and he motivated me in many things. So here are a few things which I would like to tell about him. A couple of happenings come to my mind. One was when I was studying here. I was a faculty member, but I had done my postgraduate here. Then I said I would continue with my research and do PhD here. Dr. Shankarlal was impressed with me and he said, Verma, why don't you go abroad? Because you don't only learn there, you experience something. And what you see there, they are the most modern things. And what we are doing here is something old. Actually, I can tell you that at that time we had not progressed to that level that we were current. We were really ancient in some respect. So I was motivated and I went abroad. I went to USA and I went to Duke University to work under Professor Jack Cheddar. And actually I had contacted Professor Cheddar, who was chairman of ASHRAE at that time. And he was a well-known professor in the field of refrigeration air conditioning. So Duke was the place where he had only recently shifted from Purdue University. He accepted me as a student, and I was really fortunate to have worked under him. He provided me an insight into the research activities, what is involved. It is not just working and getting a PhD degree, but an overall outlook in the research. So this was a great experience which I learned from him. When I returned to India, I wanted to utilize my experience and knowledge that I had acquired in USA. So I started writing some proposals to DS Department of Science and Technology. In this, I was very much motivated by my head of the department at that time, Dr. Shankarlal. He guided me also in many things. And the proposals that I wrote first, I was a young man. I was hardly 30 years. And when I wrote my first proposal and I got the grant, it was a great achievement for me. And then I continued. So that was the building block. And then I continued in getting involved with research, guiding my students, and preparing them for a professional career. So I started working in the department, and I started working on some projects. Dr. Shankarlal told me that you write some proposals to different funding agencies, different scientific organizations like CSIR, Department of Science and Technology. I said, I'm very young. How would I get anything from any grant or any support from them? He said, no, it is not your age. It is the content of your proposal. So I wrote something. I went to him. He moderated it, he edited it, and he said, okay, go ahead, send it. And lo and behold, I got it. And then it was a starting point of my getting grants from different organizations. I continued to get it till I retired. And I'm indebted to him in this particular respect.
Thank you very much. Sir, I took permission from you to play your video. You have to say something or anything. Yeah.
Hello.
Yes.
Actually, Dr. Shankarlal was a great source of inspiration to me. He was my teacher also for some time. Then he encouraged me to go abroad and pursue my research there. Actually, one incident that I remember, I was a young faculty member when I suggested, we used to have 8 compulsory courses in master's degree and 4 electives. So I just went to him and I said, let us have little more electives so that our students have a choice to select their own interested career. He said, we have just changed the syllabus, we have just increased the number, and I don't think I will support it. I was a young faculty member looking forward, so I sent the proposal to Board of Studies. And I later on, people said, what have you done? He's such a senior professor, you have just not agreed to his opinion. I said, now I have done it. And I was surprised that in the Board of Studies, he supported my proposal. He said, oh, although it is immature, but it will help the learning of these students, the academics of these students, of the master's students. And that made me think very high about him, because initially he was not supporting it, but then when it mattered and when he saw that it is important and helpful to the students, he supported it. So I had great opinion of him, and I worked a lot with him, and with his support, I went abroad. I did many things which were commendable. Thank you.
Thank you, Professor Verma. I take this opportunity to request Professor Ajit Chaturvedi also to say a few words and address the guardians.
Thank you, Professor Gandhi. I think the audience, all the students, faculty are waiting to hear Professor Narasimhan. But you have given me the platform, so let me share a few thoughts. This endowed lecture series, memorial lecture series, which has been initiated in every department and center of the institute, is a initiative which was taken keeping in mind several, if I may say, several goals. And of course, the first goal was that we would like to honor and remember and celebrate the success of the stalwarts of University of Roorkee, the stars which gave the name to University of Roorkee, and they will serve as an inspiration for the current generation, that how they made a mark at the international stage, how they were known by their work in the best of journals, and they were able to compete globally. All these things come to the fore in different departments, including the Department of Mechanical and Industrial Engineering. So they serve as an inspiration for the current generation. Second, equally important goal was that this could be a very good, if I may say, pretext to bring experts like Professor Narasimhan onto the campus and hear their own research and contribution and see what we can learn from them. And the third goal was that when experts come to the campus, they also get to know the several interesting projects that our faculty and students are doing. They can visit our labs, they can interact with the students, they can interact with the faculty, and they will get to know more about our department, and in turn they can spread the whatever good things are happening in the departments. And at the same time, the departments can learn whatever suggestions or feedback or comments or observations that any experts, when they come, they make. Now, this third objective is not getting met because of the COVID pandemic. So we ideally wanted the experts to come to the campus, and that is why we waited. The initial lecture was scheduled. I remember Professor Kaushik Pal making a lot of effort, everything set up, and then we initially thought we can postpone and we can still have it, but then it was not happening physically, and now it is not very clear when very safe travel will happen. So we didn't want to postpone this because this is an annual event, and now the second year has started, and we should have the second edition of the Shankar Lal Memorial Lecture. So we thought that, okay, at least we can hear Professor Narasimhan, and there can be a very candid exchange of question answer session after this talk. And maybe we can gain to the extent it is possible in online sessions, and thereby also inaugurate this Shankar Lal Memorial Series. It was very thoughtful on the department of Professor B.K. Gandhi and the entire department to bring on this occasion his contemporaries and his students like Professor H.K. Verma, Professor S.P. Nigam. That adds a touch of emotion to such inaugural functions, and I think it's very well appreciated. These things do matter a lot, and they remain in our hearts and mind for a long time to come. So I think with these words, I would congratulate the department for having finally come to this day, and let us all now hear Professor Narasimhan for his talk on this magnesium and the way the fracture takes place in magnesium, the multiple modes in the way
Thank you very much, Professor Chaturvedi.
Thank you, Professor Gandhi.
Thank you very much, Professor Chaturvedi, for all your encouragements, and because of that only, it was possible that we took the lead for this organizing this event through Webex. I know that we had kept it earlier on 17th of March, and due to pandemic, we had to cancel it out. And not we have cancelled, we have postponed it, but we wanted it physically. But still, we believe that whenever Professor Narasimhan will get a chance, he will certainly visit us, and we are very much welcome him to our department, and he can visit to all our laboratories, advise our students and faculties. In the same time, I would like to request Professor Kaushik Pal to introduce first Professor Narasimhan to us, and then he can take the presentation.
Okay, thank you, Professor Gandhi. So it's a very good afternoon to all. So it's my privilege to introduce Professor R. Narasimhan, Professor in Department of Mechanical Engineering at IISc Bangalore. Professor Narasimhan received his bachelor degree in Mechanical Engineering from Indian Institute of Technology, Madras in the year 1982, and master's and doctoral degrees from California Institute of Technology, Pasadena, USA in 1983 and 1986. After working for 4 years at Indian Institute of Technology, Bombay, he joined the Indian Institute of Science, Bangalore in the year 1991, where he is presently professor in Department of Mechanical Engineering. He received the Santi Swarup Bhatnagar Award in 1999 and was a J.C. Bose National Fellow from 2010 to 2020. His research interests are computational solid mechanics, mechanical behavior of materials, and nonlinear and dynamic fracture mechanics. He has published more than 115 journal papers and guided the thesis dissertation of about 25 research students. He is a fellow of Indian National Science Academy, Indian Academy of Sciences, and Indian National Academy of Engineering. He has served as chairman of Engineering Sciences Research Council of CSIR and as member of Science and Engineering Research Council of Department of Science and Technology. Also, he has served as member of the editorial boards of International Journal of Fracture, Engineering Fracture Mechanics, Journal of the Mechanics and Plastics of Solids, and Mechanics of Materials. So now, may I request Professor Narasimhan to start his lecture.
Thank you very much, Professor Kaushik Pal, for your very kind introduction. So let me share my screen. I'll stop my video and share my screen.
Okay, in the meantime, I request all the audience. So during the presentations, if you are having any queries, so please you write down your queries in the chat box. So after completion of Professor Narasimhan's lecture, so sir will respond all the questions one by one.
Can you see my screen?
Yes, sir. Absolutely.
Yeah. Okay, so let me begin by thanking Professor Chaturvedi, the director of IT Roorkee, and Professor Gandhi and Professor Kaushik Paul, the entire Department of Mechanical and Industrial Engineering, IT Roorkee, for giving me this unique opportunity to deliver this inaugural memorial lecture for Professor Shankar Lal. It's a great privilege. And for me, it is a very special thing because Professor Shankar Lal was an alumnus from Guggenheim Aeronautical Labs, California Institute of Technology in the 1950s. And I was also a PhD student in the 1980s from the same department. I received my PhD in the year 1986 in solid mechanics. I actually went to the Caltech archives, and I downloaded this thesis citation of Professor Shankar Lal. So you can see here, not sure whether you can read the text, it's pretty small. So it's he has worked on heat transfer in I think thermal boundary layers. That is the area in which he has done his PhD, and he worked according to this data which is there in this archives. He worked with Professor Paco Lagaston, and the thesis, if you go through the abstract, it's very theoretical work which he has done for his thesis, and the date of defense is also given there, but I'm not sure whether the date is right. 1st January 1955. So I'm not sure whether they would have held a defense on 1st January, but anyway, it was in 1955. So it is really a wonderful time to have been a student at GALSIT, because that was a time when people like Hans Liebmann and Clark B. Millikan and probably Karman had stepped down, and people like Millikan were there. So I think that was the time when fluid mechanics was at its peak in GALSIT. So it would have been a really great, wonderful experience to have been a student at that time. And as you know, there are other eminent scholars in the country who also graduated from the same department at the same time, around the same time. Professor Satish Dhawan was also a student of GALSIT, probably around the same time. All right, so with that little reminiscence about connections with GALSIT, let me turn to the topic of my presentation, which is going to be on mechanics and mechanisms of fracture of magnesium alloys, a topic in which I've been working for the last 10 years or so. Let me begin by first acknowledging my collaborators, my former PhD student, Subramanya Prasad Narla, and my current PhD student, Vaishak, my colleague in materials engineering, Professor Satyam Suvas, with whom I've been collaborating quite extensively on this topic, my former master's student, Kaushik, who later went and did his PhD at Brown University, and now he is employed in GE Global Research in New York. Dr. Raj Mishra from General Motors R&D Warren Labs, Michigan, who actually introduced me to this topic of magnesium deformation and fracture. Now, magnesium alloys have been attracting a lot of attention in recent years for a variety of reasons. The most important being that they have low density and high specific strength, and they also have good damping characteristics and machinability. So in view of this, they are being considered as economic replacements for aluminum die castings, cast iron, and steel components in automobiles. If you take a look at the photograph on the right side, that is an inner door frame made from magnesium alloy. On the flip side, magnesium has poor corrosion resistance. Its room temperature formability and fracture toughness are not as good as aluminum alloys. Another very characteristic feature of magnesium is that, being a HCP metal, it doesn't have adequate number of slip systems to accommodate arbitrary deformation. So therefore, plastic slip happens by a combination, plastic deformation happens by a combination of slip and twinning. It's highly anisotropic. And one of the manifestations of that is tension compression asymmetry. At room temperature, magnesium has 18 slip systems and 12 twin systems. I have shown that in this slide, and I've also indicated the number of systems per type, as well as the critical resolved shear stress pertaining to each of these systems underneath each figure. The top panel, comprising of basal slip, prismatic slip, and pyramidal slip A, these cannot accommodate deformation along the C-axis of the hexagonal lattice. It requires activation of one of the systems from the bottom panel, which involves pyramidal A plus C slip, tensile twinning or 101 bar 2 type, and contraction twin or 101 bar 1 type. The tensile twins, the reason why they are called tensile twins is because they cause extension along the C-axis, whereas the contraction twins cause contraction along the C-axis. The tensile twins can widen very rapidly. They can engulf entire grains, as we are going to see in some of the slides subsequently. Contraction twins, on the other hand, remain typically narrow. Both of these involve very large rotation of the crystallographic lattice when they take place. Now, if you examine the critical resolved shear stress values, which I have listed here, you would note that basal slip and tensile twins have very low critical resolved shear stress. They are soft deformation modes, whereas pyramidal C plus A and contraction twins, on the other hand, are hard deformation modes. Let me show one very important result from the literature which would actually motivate our work. And this is a study on the effect of stress triaxiality on ductility and the failure mechanism in a rolled AZ31 magnesium alloy. And this is from the work of Kondori and Benzerga. And they actually worked with, they did tension tests on smooth and notched cylindrical bars cut from a hot rolled AZ31 magnesium alloy. What you see in this slide is the fracture surface corresponding to a sharply notched Rn2 specimen, which has got a triaxiality. The triaxiality T is defined here as the ratio of the mean stress to the equivalent stress, sigma m by sigma e. So the Rn2 specimen has a triaxiality of around 1.5. And if you examine the fracture surface, you can see that there are some grooves or flutes, elongated groove-like features, which are associated with the cleavage type mechanism, basically twin-induced microcracks. On the other hand, if you look at the right side micrograph, which pertains to a shallow notched Rn10 specimen, which has got a lower triaxiality of around 0.8, we see ductile void growth and coalescence. So there is a transition in the fracture mechanism as the triaxiality decreases. Also, the bottom figure shows the strain to failure. And we can see the strain to failure is maximum corresponding to moderate triaxiality, Rn10 specimen, around 35% ductility, and then it decreases very sharply with the increase in triaxiality. Now, similar brittle to ductile transitions with reduction in triaxiality have also been observed in other magnesium alloys like AM60 and AZ91. Now, with that little introduction, let me turn to the objectives of our work. Since tensile twinning, essentially, although contraction twins are also important, have been shown in the literature to play a very pivotal role on the deformation and failure in magnesium, we wanted to understand this more closely. So we wanted to begin by doing fracture experiments using magnesium single crystal specimens and understand how tensile twinning develops and what's the effect on the fracture resistance. The reason why we chose magnesium single crystals is because it's easy to vary the lattice orientation and understand the effect of also individual twin and slip systems more easily when you work with single crystal specimens. Next objective was to look at a polycrystalline AZ31 magnesium alloy, very commonly used wrought alloy. And again, here, here the effect of notch root radius, namely the stress triaxiality, and mode mixity, that is combination of the tensile mode, mode 1 of fracture, and the in-plane shearing mode, mode 2, on twinning development and fracture behavior was to be investigated. And the last objective, which I'll be describing today, is some finite element simulations of void growth and coalescence in magnesium single crystals. So here we have carried out simulations using unit cell models as well as wide growth and coalescence ahead of crack tip in the fracture process zone. Let me first show some results from our fracture experiments using magnesium single crystal specimens. And these were conducted using three-point bend specimens, which were tested inside a scanning electron microscope with provision for electron backscattered diffraction to make in situ observations. As I said, one of the ideas was to look at the lattice orientation. So we considered 3 lattice orientations in what I'm going to call as A and B, which is shown on the right side schematics. The C-axis, which is the 0001 axis of the hexagonal lattice, is along the normal to the flat surface of the notch, while the direction ahead of the tip and along the crack front, those are switched around between these 2 geometries. If you look at orientation C, the C-axis along the thickness direction. The dimensions of the specimen are listed at the bottom. The width of the specimen is about 4 mm, the span about 24 mm, thickness around 1.6 mm. And the notches in these specimens were cut using electric discharge machining, EDM, to a diameter of about 400 microns. The crack length to width ratio, A by W, is about 0.5. These are electron backscatter diffraction maps, EBSD maps corresponding to orientation A. I have shown at the bottom left side. Now remember, in orientation A, the C-axis along the normal to the flat surface of the notch, as you can see in the schematic on the left side top. On the bottom left side, we see the inverse pole figure map of the as polished specimen. And we can see a strain-free surface in this case. The right side sequence of images are image quality maps obtained from the EBSD data corresponding to different stages of deformation, load point displacements delta. And here the extension twins, the TTs, are colored red, the 101 bar 2 twins. So if you take a look at the sequence of images, very early during the deformation, 2 twins W and B nucleate at the notch root, and with increasing deformation, they both widen as well as extend. However, as the deformation proceeds, you can see at the bottom right side image, multiple intersecting twins have nucleated, and some of these obstruct the extension of the initial twins. So the width of the initial twins increases and then saturates at around 120 to 140 microns. In the case of orientation B, the development of twinning was very similar to what I showed in the last slide. So there also the C-axis along the normal to the flat surface of the notch. But it turned out that in all the specimens which we tested for orientation B, there were some polishing twins which were present, and these sort of impeded subsequent twin development and led to premature failure. I'll mention about that a little later in my presentation. But here, let me turn to the other orientation, orientation C, where the C-axis, as you can see in the schematic, the 001 axis is along the direction of the notch front, that is along the thickness direction. Again, taking a look at the IPF map of the as polished specimen at the bottom left side, you can see a strain-free surface in this case. And then examining the sequence of IPF images on the right side corresponding to different load point displacements, we can see a different pattern of twin development which is taking place. Unlike in the case of orientation A and B, where the twinning started from the notch root and started emanating out from the notch root, here we see that it commences at the far edge of the specimen, where there is there's a compressive global bending stress field, which in this particular orientation is favorable for extension twinning. And that set of twins propagate towards the notch root, as you can see by following the sequence of images. And at very large load point displacement, however, there is a region identified as R in my bottom right side image, which is still free of twins. And we also see 3 twin variants in this case, as opposed to the other case where we saw 2 twin variants. Now, one of the things that we wanted to investigate, and this has very rarely been looked at in the literature, is whether some of these twins persist through the thickness. Do they have a 3-dimensional character? So in order to do that, we unloaded some of our specimens and then chemically etched and polished them down to the quarter plane and the mid plane, and then subjected the specimens to EBSD analysis. I have shown here on the top sequence of images image quality maps from an unloaded specimen corresponding to orientation A, the free surface, the quarter plane, and the mid plane. And if you examine these images, you can see the pattern of twin development is very similar. There's not much thickness dependence. In fact, some of the twins like the W and V twin, which I showed in my earlier slide, they seem to persist all the way through the thickness. We quantified the average twin volume fraction by marking out a rectangular region PQRS, as I've shown in this diagram, about 900 microns in size, and then used ImageJ software to quantify the twins, the twin areas, then calculated the average twin area fraction. And in the table at the bottom, if you examine that table, you can see that at this stage, there is not much dependence on the thickness as far as the twin area fraction is concerned for this orientation, around 25% everywhere. On the other hand, if you look at orientation C, which is the shown at the bottom, the IPF maps on the free surface and the mid plane, you see a more pronounced thickness dependence, with the mid plane showing more profuse twinning as compared to the free surface. So the average twin area fraction is about 89% in this case from the unloaded specimen for the mid plane, whereas it's around 78% for the free surface. There's a bit more dependence on the thickness in this particular case. Let us look at optical metalograph in order to understand the type of slip traces and twin traces as well as the crack path. This slide pertains to orientation B, where remember again the C-axis is normal to the flat surface of the notch. If you look at the left side image, the optical micrograph on the left side, we can make out two slip traces, S1 and S2, which I have marked. The S1 slip trace, which is parallel to the notch flank, pertains to basal slip. The S2 slip trace, which you can see near the extended crack, which are horizontal, those pertain to prismatic slip. Also, you can see traces of two twin variants, which are intersecting ahead of the crack tip. And a very interesting feature is if you follow some of the basal slip traces, take a look at the image, optical image on the right side top. If you follow the line KJIH, that line KJIH deflects by almost 90 degrees inside a twin. And then again, it deflects back by 90 degrees as it exits the twin. So this suggests this is due to the lattice rotation inside the twin, and this suggests strong secondary slip activity taking place inside the twins. Now, in all our experiments, the crack initiates before the peak load, and it grows stably along the twin boundary. And when it reaches the intersection between two twins, it gets deflected. You can see that in the right side image very clearly, top image, MN and NO are the two segments. The deflection has taken place at point N at the intersection between two twins. We can make that out even more clearly on the bottom left side, which is a scanning electron microscope image, where you can see the deflection of the crack as two segments, MN and NO. And also you can notice at point N, the crack couldn't actually take a decision whether to continue along its original path as a segment NP or to get deflected as NO. Eventually the segment NP, there's a forking there taking place. NP actually arrests and the crack then begins to grow along NO. This is one of the things that we would like to understand by doing some numerical modeling. I'll describe that briefly a little bit later. The bottom right side image is a SEM fractograph, and we see very intriguing features of some elongated stripes. Now, we believe that, like I marked some of them as RS and TU, we believe that these are due to intersections of twins of the other variant on the fracture surface. We sought the twin-twin intersection in the optical metallographs as well as in the EBSD images. We quantified the average twin area fraction as a function of load, as I described earlier, by marking out a rectangular region about 900 microns, a very large region, 900 microns in size, and then evaluated the average twin area fraction using the ImageJ software and plotted it against load corresponding to the three orientations. That is the picture, the figure which you see on the left side. And the right side is the energy release rate, the J, plotted as a function of load. Now, if you examine these two figures, you see a qualitative similarity between the two. In particular, if you look at the twin area fraction evolution for orientation A and B, they are similar, except that in the case of orientation B, you will see that FTT, the average twin area fraction, starts from a finite value. This is because there are some polishing twins which are present in the specimen, as I mentioned. And also, it tends to saturate early, and that is owing to the impediment caused by the polishing twins to subsequent twin development. This also led to premature failure, as you can see on the right side. The circular symbols indicate the stage at which the specimen failed. The qualitative similarity between the twin area fraction near the notch tip and the energy release rate histories suggests that tensile twinning is an important dissipation mechanism and can therefore enhance the toughness. In order to understand the experimental results more clearly, we also did complementary numerical simulations, finite element simulations, using crystal plasticity model, single crystal plasticity. So the kinematics involved is illustrated in this slide. The classical crystal plasticity formulation is due to Asaro and Rice, which is shown on the left side, and this was modified for treating twinning as a quasi-slip process by Khalidindi and Starosolsky and Anand, and that is shown on the right side here. Both these formulations involve a multiplicative decomposition of the deformation gradient into an elastic part Fe and a plastic part Fp. If you take a look at the left side schematic, in the case of the Asaro-Rice formulation, Fp takes into account plastic shearing on crystallographic slip systems, whereas Fe accounts for the rotation and the stretching of the lattice. In the Khalidindi Starosolsky-Anand formulation on the right side, Fp accounts for slip in the untwinned region and twinning in the untwinned region, which is called as primary slip and primary twinning, whereas the stretching and the rotation of the lattice are vested in Fe. The flow rule is written, as you can see in this slide, for the plastic part of the spatial velocity gradient, LP, given by the equation on the top of the slide, and it involves contributions from slip in the untwinned region, the first term of on the right-hand side of this equation, and twinning in the untwinned region, which is the second term in the RHS. Now, in these equations, capital S represents the Schmidt tensor, gamma is the plastic slip, gamma TW is the twinning shear, which is around 0.13 for extension twins, around 0.14 for contraction twins in the case of magnesium, and F alpha is the twin volume fraction. Now, at a certain continuum material point, the contribution to the average Cauchy stress arises both from stress in the untwinned region and the stress in the twin region, as you can see from the equation given in the middle of the slide. In our calculations, we made use of the hardening and evolution laws for plastic slip and twinning. These are phenomenological laws given by Zhang and Joshi. And one of the hallmarks of their work was they actually benchmarked these parameters against channel die compression experiments of Hosford and Kelly corresponding to 6 or 7 orientations for magnesium single crystals and tuned their material parameters. So we used all that values in our models, in our analysis as well. And we implemented this model in our own in-house finite element code using the rate tangent modulus formulation of Pierce, Asaro, and Edelman. We implemented this within the framework of a finite deformation, finite element procedure, B-bar based finite deformation, finite element procedure to treat nearly incompressible deformation in the fully plastic range. This is a finite element model of the single crystal specimen. We did 3D analysis, and because in all these specimens, all the orientations, there is both crystallographic symmetry as well as mode 1 symmetry. We consider half the specimen through the thickness and half along the length. And in-plane views of the mesh, as well as the detailed view near the notch root, as shown here, we model half the specimen through about 7 element layers. And these get increasingly thin as we approach the free surface in order to capture the steep stress gradients as you approach the free surface. These are load displacement plots from the numerical simulations which are compared against the experiments for the 3 orientations. we see a reasonable agreement between the two, and both sets of analysis, experiments as well as simulations, show a bilinear response with very high hardening. And this hardening is associated with twinning, essentially, tensile twinning, various mechanisms which are invoked by twinning, like twin-twin intersections, twin-slip intersection, texture hardening. All these result in very large hardening. One of the things that you can see in these experimental curves is some serrations in the load displacement curves. And these are associated with nucleation of discrete twins. So whenever a discrete twin nucleates, it leads to a drop in the load, and that is because of increase in tensile strain. That's not captured in the simulation because the simulation assumes twinning as a quasi-slip process. These are contours of twin volume fraction corresponding to orientation A and orientation C. And what I have shown here is the contours on the free surface of the specimen at the midplane, as well as through the thickness on the right side, taken on a plane ahead of the notch tip. Those are the three images which you see in each row. The top row is for orientation A and bottom row is for orientation C. And we note again that in A, the C-axis is along the normal to the flat surface of the notch, C-axis along the thickness direction. So if you look at the top panel, you can see that the twin volume fraction is developed in a roughly rectangular region emanating out from the notch root. And there's not that much thickness dependence. If you examine the image on the top right side and the twin volume fraction contours, there's not much variation through the thickness as you go from the midplane to the free surface. On the other hand, if you look at the bottom side, you see a different pattern of twin volume fraction development. It starts at the far edge of the specimen and then approaches the notch root. And there's a region near the notch root which is free of twins, as we saw in the experimental EBST images. And also there is more distinct thickness dependence, which we can make out clearly on the image on the right side. So therefore, the simulations do capture some of the essential features of what we saw in the experiments. We also quantified the average twin volume fraction by considering a rectangular domain in the finite element model, which is marked out here as this EFGHI, and calculated the average twin area fraction, plotted it against load, and compared with the experimental data. And we see a reasonably good agreement for orientation A and C, whereas in orientation B, there are some differences. And these differences are attributed to the fact that in the experiments, there were some polishing twins, which, as I said, impeded subsequent twin development, which is not captured in the simulations. One of the things that we wanted to understand, as I pointed out in the earlier slide, is that the deflection of the cracks at the intersection between two twins, what is the origin for that? Now, in order to investigate this, we took some two discrete twins from the exact variants which we saw in our experiments corresponding to orientation A, and put them in our FEM model. So that's what you see here. So two discrete twins, 1 and 2, which are intersecting along a line AB. And if you look at the left side mesh, this pertains to the initial configuration where from the notch root, the crack is extended along OA with a tip located at point A. In the case 1 simulation, we assume the crack to extend along the twin boundary, the boundary of twin 1, without any deflection, with a crack tip located at point B. Whereas in case 2 simulations, we take the crack to have deflected at point A and to have extended along AC with the tip located at point C. The analysis conducted here are plane strain finite element analysis using the same crystal plasticity theory, which I described. The energy release rate is computed as the rate of decrease of the strain energy with respect to crack area. Before I show the energy release rate variations, let us take a look at contours of equivalent plastic slip for the initial configuration, the contour plot on the left side in this slide, and the case 1 simulation, the contour plot on the right side. The crack tip locations are indicated in both the contours. And the interesting observation here is, if you look at the right side contour plot, there is more intense plastic slip concentration at the intersection between the two twins rather than at the current crack tip. And you can actually see the crack has opened up along the twin boundary. And furthermore, we see slip development, plastic slip development inside the twins, the secondary slip activity, which we saw in our optical metallograph. That is again evident from these numerical simulation results. The most emphatic thing in our model, in our simulation, is this plot here, which shows the energy release rate versus load point displacement corresponding to the two cases. Case 1, remember, is the situation where the crack is allowed to grow along the twin boundary without any deflection, and case 2, where the crack is taken to deflect at the twin-twin intersection. So this clearly shows the energy release rate for case 2 is much higher compared to case 1, almost by a factor of 2, corresponding to load point displacement of about 0.25. So this establishes that crack deflection would be favored at twin-twin intersections from an energy release rate standpoint. Now let me summarize the key takeaways from this part of our work. We noticed profuse tensile twinning occurring ahead of the notch tip in all the orientations which we studied. But the pattern of twin development depends on the lattice orientation, as we saw the difference between orientation A and orientation C. In all the experiments, the crack is seen to grow stably along the twin boundary, getting deflected at twin-twin intersections, which we showed from our Feinkelman analysis to be favorable from the standpoint of energy release rate. And perhaps the most important takeaway is the fact that tensile twinning is an important dissipation mechanism. Its evolution near the notch root correlates well with the energy release rate history. So that establishes that this is to be considered as a mechanism that can enhance the toughness. And we will see more of it in the polycrystals experimental work, which I'm going to show next. So now next, let me turn to some experiments which we did using rolled AZ31 magnesium alloy. Here we conducted experiments using both compact tension and 4-point bend specimens, thickness around 10 mm. And one of the ideas here was to look at the effect of stress triaxiality. Triaxiality is a very important factor as far as fracture of magnesium is concerned. So we varied the notch root radius and considered different EDM cut notches, as well as fatigue pre-crack specimen FPC in our experiments. What you see on the left side is the inverse pole figure map of the as polished specimen, and the right side are pole figures 001 and 101 bar 0 pole figures. The IPF map shows a nearly basal texture with most of the grains having the C-axis along the normal to the flat surface of the notch. But there is some deviation from an ideal basal texture. We can make that out clearly if you look at the pole figure on the 001 pole figure on the right side. The intensity, the red region, is not exactly at the center, which is the ND, but a little offset towards RD. This deviation we found is less in the midplane of the specimen as compared to the free surface, and we believe that this is attributed to the rolling operation. The average grain size for this alloy is around 14 microns. The student who worked on it, Prasad, who is I think there in the audience, did a very thorough job, and he stitched together several optical metallographs and came up with this schematic on the right side, which depicts the twin development over the entire specimen, and it is ubiquitous, as you can see there. There's twinning all over the specimen, especially in the ligament at the far edge of the ligament at location B, near the notch tip at location A, above and below the notch tips taking place. Now, the left side set of images are inverse pole figure maps taken at two locations, at point A, which is very close to the notch root, point B, which is at the far edge of the ligament. And at point A, Prasad took the scans both in the midplane as well as the free surface. They are shown on the top image and the one in the middle. The bottom one is taken at the free surface at location B. Now, in all these images, all the IPF maps, we can see presence of thick extension twins, 101 bar 2 type twins. And comparing the top IPF image with the middle one, we see more profuse twinning in the free surface compared to the midplane in this case. And that's because of the texture difference which I noted in the last slide. In the mid plane, if you look at the top IPF, you'll see that twins are present mostly in the large grains, like the ones labeled as O and Q, and this possibly because of reduced critical resolved shear stress for twinning in these large grains. There is actually a wealth of information about how twinning can influence hardening and fracture mechanisms by examining these pictures. Specifically, if you look at the top IPF, you can see there is a continuous chain of twins cutting across grain boundaries. For example, close to grain Q at the top IPF, you can see a chain of twins which are extending across multiple grains. The middle IPF shows intersection of twins in some grains. For example, in grain L, you can make out intersection of two twins. And coalescence of twins of the same variant in some grains, for example, grain M in the middle IPF. The bottom figure shows some of the grains having completely been engulfed by tensile twins, for example, grain D and grain G. So this establishes the significant dissipation happening because of extension twins over the entire ligament. Now, these are optical metallographs corresponding to different notch root radii taken from the 4-point bend specimens. And in all the images, we can see twins are present in the grains surrounding the crack tip. We actually quantified this by considering several 100-micron size domains. Prasad did a very systematic job again and calculated the average twin area fraction by doing very painstaking metallographic work, and found that the average twin area fraction increases from about 4 to 14% as the notch root radius decreases from 175 microns to the fatigue pre-crack specimen, which is shown on the bottom right side. That is the FPC or the fatigue pre-crack specimen. Now, taking a look at this FPC specimen, if you closely observe the ahead of the crack tip, there is a slit-like void, which we have labeled as W, and this is presumably associated with the twin-induced crack that has formed. On the other hand, if you examine all the other optical images pertaining to the pre-notch specimens, you would notice that there are some oblate voids. For example, if you look at the top left image corresponding to the 175 micron notch root radius, you'll see two voids P and Q, which have actually coalesced with each other, and they're about to coalesce with the tip as well. These are SEM fractographs, again from the 4-point bend specimens corresponding to different notch root radii. Again, examining the fatigue pre-crack specimen at the bottom right side, if you look at the morphology, fracture morphology, we can see some elongated grooves or splits similar to what Skondori and Benzerga observed in their sharply notched tensile bar specimens. And these are evidence of cleavage 3 mechanism operating, presumably due to twin-induced cracks. On the other hand, if you look at all the notched, pre-notched specimens, you would notice that there is dimple fracture, and some of these dimples actually have inclusions sitting inside them. We can see that more clearly from the X-ray microtomograph image on the right side, which shows dimple fracture on the specimen surface and numerous gray or white colored dots, which are actually second phase particles. Some of these have triggered the void growth, as we can see in the SEM fractographs. We also did an EDS spectrogram of some of these particles and found that these are mostly manganese-rich particles. And one of the observations which we could make is that the average dimple size, again through very painstaking metallographic characterization, the average dimple size increases from about 29 to 40 microns as the notch root radius increases from 60 to 175 microns. These are EBSD maps from the 4-point bed specimens taken at the far edge of the specimen for 2 specimens, and you can see profuse tensile twinning with most of the grains having completely reoriented, and the pole figure shows a basal to prismatic change in the texture, very, very vast texture change as compared to the initial pole figure, which is shown at the bottom. Now let us take a look at the energy release rate, the notched fracture toughness versus the notch root radius. And I have also affixed the SEM fractographs so that we can correlate the toughness with the fracture mechanism. Beginning with the very pre-cracked specimen on the left bottom, we note that this has failed by a cleavage type mechanism due to twin-induced cracks, and the toughness is low. As the notch root radius increases beyond about 30 microns, there is a transition to a fibrous mode of fracture, and the wide size, as I noted, increases, and this is accompanied by a very large increase in the toughness. We used a simple model based on the classical Rice-Johnson theory and coupled it with the Rice-Tracy wide growth equations in order to predict this experimental trend. And the predictions are shown here by the plus symbols, and you can see that the predictions match with the experiments pretty well. Here is how the model works. Very briefly, the Rice-Johnson model involves the growth of a initially spherical void of radius R0 in the blunting fields ahead of a notch tip. And at a particular stage of deformation, it has become ellipsoidal in shape with the principal radii R1 and R2. We assume that this void has nucleated from an inclusion when the mean stress sigma m, which is given by this logarithmic expression here from the logarithmic slip-line field, reaches a critical value sigma c. This gives rise to a relationship between the nearest void nucleating particle L0 and the notch root radius by the equation in the middle of the slide. And following the Rice-Tracy wide growth rate equations, which were approximately integrated by Thomason, we can write the sum of the principal radii as related to the initial notch root radius, wide size R0, through this expression 2f times R0, where f, the parameter, exponentially depends on the normal strain as well as the mean stress. The Rice-Johnson assumption of coalescence of the void with the crack tip takes place when the distance between them becomes equal to the sum of the principal radii. We applied that criterion and came up with the equation in the box for nonlinear algebraic equation for the parameter alpha, which is rho divided by delta Tc, the notch root radius divided by the critical crack tip opening displacement. Now we solve this equation numerically using the Rice-Johnson slip-line solution for the plastic strain field ahead of the tip, and determine the delta Tc, the crack tip opening displacement corresponding to different notch root radius, related it to the near tip Jc by the expression at the bottom of the slide, combined it with the dissipation contribution JCO, which we approximately inferred, and plotted it against rho, and that's what you see here by the plus symbols. So the model seems to work pretty well in predicting the trend. Now let me spend a few slides on some very recent experiments which we have done on mixed mode fracture of magnesium, and this was conducted again with 4-point bench specimens with the rolling direction along the span, TD along the width of the specimen and ND along the thickness. So the characteristic specimen geometries are shown on the right side. In the symmetric 4-point bench specimen, the rollers, loading and support rollers, they are placed symmetrical with respect to midplane. In the asymmetric mixed mode specimen on the bottom right side, these are placed asymmetric, and also the crack plane deviates from the midplane of the specimen by a certain amount D. By varying that D, by reducing that D, we can induce more amount of shear loading at the tip. The mode 2 component increases as D decreases, as you can see from the table on the left side. And this is quantified to what is called the elastic mixity parameter ME, which is defined in terms of the ratio of K1 to K2. Now we did optical in situ imaging as we loaded up the specimen, which was later analyzed by DIC in order to figure out the strain distribution as well as the crack opening and sliding displacements. So this slide shows the way the energy release rate versus the load. So we computed the total energy release rate by taking the mode 1 and mode 2 contributions, using the moment versus the specimen rotation and the shear force versus the notch mouth sliding displacements, using a procedure which we derived in a paper in Inaugural fracture last year. And the total energy release rate is plotted against load on the right side. As we go towards mode 2, the specimen experiences larger levels of load. The crack initiation stage is indicated here by the dots. These key results are summarized in the table here. We also introduce here a definition of plastic mixity, MP, based on measured values of near tip opening and sliding displacements of the crack tip, which is indicated by the equation on the left side. So the most important observation from the table is that as we decrease the mode mixity and as we approach mode 2, the notch fracture toughness diminishes quite extensively, almost by a more than by a factor of 2. And also the plastic mixity, near tip mixity, is lower than the elastic mixity, and that's due to intense shearing which is taking place in this specimen. We can make that out from optical metallographs, which I have shown here for the mode 1 specimen on the left side, the mixed mode specimen in the middle, and the mode 2 specimen on the right. So if you look at the mode 1 specimen, the notch actually blunts symmetrically, crack initiates at the original notch tip and goes straight. In the mode 2 case, in the mixed mode case, one portion of the notch root sharpens and the other portion stretches. The crack actually initiates in the stretched part and then it grows at an angle, as you can see in the right side middle image. In the mode 2 case, there is acute sharpening of the notch tip, and there are 2 branches of cracks which initiate. The portion C2D2 at the sharpened part, it grows a little bit and it arrests, whereas the C1D1 branch initially grows at an angle, then it curves around and goes straight ahead of the crack tip. These are von Mises strain contours for mode 1 and mixed mode case in the middle and the mode 2 case. So in the mode 1 case, there are strains developing symmetrically as 2 lobes about the notch tip on the left side. These curve around and then they link up. If you see the top left side, a triangular region of large strain, which is caused by the compressive bending stress field. In the middle image for the mixed mode specimen, the left lobe has rotated clockwise and extending straight ahead of the tip, whereas the right lobe is still remaining normal to the flat surface of the notch. In the mode 2 case, there's much less twinning at the far edge of the specimen as compared to the mode 1 case. And also strain is mostly focused around the notch tip. Taking a look at the fractographs, in this case, we again notice transitions in the fracture mechanism. The left side fractograph is for the mode 1 case, and here is essentially dimple fracture with a lot of inclusions sitting inside the dimples. In the mixed mode case in the middle, we see a hybrid mechanism involving twin-induced microcracks, which are those elongated grooves or slits, as well as some small voids. And in the mode 2 case, we see a heavily sheared fracture surface, and this is because there's possibly some rubbing of crack faces, closure of the crack, and rubbing of the crack faces taking place. We quantified the average void size as a function of mode mixity for different specimens, and we noted, we can also see that by comparing the left and the middle image, the average void size actually decreases as the mode mixity drops from mode 1 to the mixed mode case. These are EBST maps taken at the far edge of the specimen in that brown rectangular region, which you see on the schematic on the left side. Again, for mode 1, mixed mode, and mode 2 case. And I have also affixed the strain contours, von Mises strain contours on the top. If you compare the 3 different cases, in the mode 1 on the left side, you see again almost all grains are completely reoriented. And the texture shows massive changes. The bottom pole figure shows basal to prismatic change in the texture. In the mixed mode case, we took the scans at 2 locations. We look at the top right side, middle image in the DIC map. We have marked location A, which is inside the strain band, and B, which is just outside the strain band. So if you look at location A, the EBST map is very similar to the mode 1 case. Lot of grains completely reoriented, massive texture change. On the other hand, if you just step a little bit out of that strain contour band and take an EBST scan, what you see on the right side, middle, you see much less twinning and much less texture change. Going to the mode 2 case on the right side, extreme image, much less strain at the far field and far few twins and far less change in the texture compared to mode 1 or mixed mode case. So with increasing mode 2 component, the texture changes at the far edge of the specimen associated with twinning, as well as the strain concentration at the far edge of the specimen, these diminish as you go towards the mode 2 case. Now let's try to understand the dependence of notched fracture toughness JC with the mode mixity by piecing together all this information. So I plotted the JC against MP going from the mode 1 case on the right side to mode 2, and I've also added the SEM fractographs as well as the von Mises DAC strain contours so that we can take a wholesome view of what's going on. So in the mode 1 case on the right extreme top, remember that failure happens due to ductile void growth and coalescence. Lot of dissipation caused by twinning, as you can make out from the strain contours, leading to high toughness. And as you transfer towards the mode 2 case, mixed mode case, there is a transition to a hybrid mechanism with more brittle features, twin-induced brittle features seen on the fracture surface, as well as less amount of dissipation caused by twinning in the background plastic zone. And as you go further down towards the mode 2 case, far less twinning-induced dissipation and shear mode of failure. So the combination of these two factors, transitioning in the fracture mechanism, as well as less amount of dissipation caused by twinning, is the reason, possibly the reason for the large change in the toughness as you go from mode 1 to mixed mode. I have summarized the key takeaways from this part of the work, but in the interest of time, I will just move further and show some few results from our finite element modeling, trying to understand how void growth and coalescence takes place in magnesium. And this again is restricted to single crystal simulations. The reason being, when you model single crystals, you can vary the lattice orientation very easily. And that gives you a perspective from the context of individual grains where the lattice would change. And we could understand it better. So from the context of texture engineering, it would be better to look at single crystals. So that's the reason why we work with single crystal. We do single crystal simulations. So these are plane strain simulations with the first with the unit cell, square unit cell with the circular cylindrical void placed at the center of the cell, subjected to different macroscopic stress ratios, sigma 1 by sigma 2. And in these simulations, we make use of the crystal plasticity model, which I described earlier, along with those hardening laws I mentioned. Two different lattice orientations were modeled. In orientation A, the C-axis is along the out-of-plane direction, that is the thickness direction. In the case of orientation B, it's along the maximum principal stress direction, X2 direction. These are contours of plastic slip corresponding to orientation A for large lambda of around 0.8 stress ratio. The top figure, and the bottom figure is for lambda 0.2, that is low stress ratio. Now, in this particular orientation, prismatic slip is predominantly active, and we can see at the top contours, at low strain, prismatic slip starts developing around the white surface, and as the strain increases, macroscopic strain increases, the prismatic slip engulfs the entire transverse ligament, leading to its necking. As you go for lower stress ratio, the bottom images, we see that initially the prismatic slip develops as an inclined band, cutting diagonally across the unit cell. But as the strain increases, again it focuses or localizes on the transverse ligament, leading to its necking. So we use the criterion based on transition to a uniaxial straining along the X2 direction to determine the stage at which void coalescence takes place. Now looking at orientation B, where remember the C-axis along the maximum principal stress direction, in this case, different slip and twin activities are triggered before the lattice reorients due to twinning. Basal slip and extension twinning are active, as you can see from the top two contour plots. Basal slip emanating out from the white surface, tensile twin volume fraction contours starting from the lower corner of the cell, and as the strain increases, it engulfs a major portion of the cell, as you can see in the bottom right side image. Now, once that happens, the lattice reorients and it triggers additional slip activity. particularly the hard slip system like pyramidal C plus A gets triggered. And you can see that evident in the left side bottom image, where it has formed slip contours, plastic strain contours on the transverse ligament. And ultimately necking of the ligament takes place, transverse ligament takes place. And one of the features of this is that it leads to a lot of texture hardening, as we will see from load displacement plots. These are contours of twin volume fraction and plastic slip corresponding to low stress ratio, again for orientation B. And again, at small strain, if you look at the contours at the top, in this case, basal slip and tensile twin are initially active. And as the strain increases, extension twins completely engulf major portion of the cell. And one of the things that happens is that prismatic slip and pyramidal C plus A slip, which get triggered, lead to shear band induced coalescence as opposed to transverse ligament necking. So on the left side image, you can see shear bands which are crisscrossing the unit cell, and they actually lead to asymmetric deformation as opposed to other cases where the deformation continues to remain symmetric. Okay, now these are line plots of the macroscopic mean stress and void volume fraction corresponding to orientation A and B. In the case of orientation A, the macroscopic mean stress develops very similar to isotropic plastic solids. So if you look at the left side plot, the macroscopic mean stress in the cell increases very rapidly, and then as the cell is no longer able to, the hardening in the cell no longer is able to compensate for the rapid expansion of the void, it reaches a peak, and then the mean stress begins to drop. And that mean stress peak value, as you can see in the various contours, various line plots, it decreases with the decrease in lambda. In the case of orientation B, if you look at the right side plot, you see a different picture here. The mean stress grows very slowly till the pre-twinning, during the pre-twinning stage, that is up to a strain of about 6%. And then there's a very steep increase in the mean stress as the lattice reorients and as hard systems get triggered, like pyramidal C plus A, then it reaches a peak value and then begins to drop. This also manifests in terms of the void volume fraction variation. If you look at the bottom two figures, in the case of orientation A, the void volume fraction evolution simply gets retarded as lambda decreases, just like it would happen in isotropic plastic solids. Whereas in orientation B, during the pre-twinning phase, there is a marked retardation of void growth rate, and that is because of activation of fewer slip systems and due to high hardening imparted by twinning. But once the reorientation of the lattice happens, additional slip systems get triggered and the void growth rate increases. And also the strain to coalescence in the case of orientation A decreases as the stress ratio lambda decreases. Whereas in the case of orientation B, this happens up to lambda 0.4. And then between 0.4 and 0.2, there is an inverse effect with the strain to coalescence dropping. And this is because of the change in the coalescence mode, which I noted earlier. Now, the last two slides in my presentation is going to be on some results from our specimen analysis using magnesium single crystals. And we analyzed two different geometries, single edge notch subjected to tension and 4-point bend. Again, two orientations, orientation A where the C-axis along the thickness direction, and orientation B where the C-axis is along the normal to the flat surface of the notch. And one of the features of our modeling is that we incorporate the set of void edge cells, array of square void edge cells in the fracture process zone ahead of the tip, so that we can look at how void evolution takes place in the FPZ in the simulation. These are square cells with each cell having a circular void at its center. The evolution of slip and twinning is quite similar in both the specimen geometries. So I'll just show very representative results. So these are for single-edge notch tension specimen. And you see a sequence of plastic strain contours as the energy release rate J increases. So in this case, as we saw from the unit cell simulation, prismatic slip is basically active. And as the J increases, it is restricted to the row of voids ahead of the tip. So these voids progressively deform into oblate shapes, strain localizes in the ligament, and then they keep necking down. So there's a void by void growth mechanism which is active for this orientation. On the other hand, we see a different picture for orientation B, where the C-axis along the normal to the flat surface of the notch. So here, if you look at the plots for low energy release rate, the top set of images, initially basal slip and tensile twin volume fraction are evident from the top two images taking place in the cells ahead of the notch tip. At large J, if you look at the bottom left side image, that red shaped contours in the FTT, those are complete reorientation of the lattice due to being engulfed by extension twins. Now, this triggers, as I noted from unit cell, additional slip activity, like pyramidal C plus A. You can make that out in the right side middle image, which are forming as shear bands crisscrossing across the fracture process zone. And this leads to intense shearing. And some of the voids here have deformed into highly prolate shapes, and coalescence would take place by void coalescence, by shear localization. Now, these are some of the key takeaways from this part of our work. Instead of going through this in greater detail, let me conclude this talk, since we have reached the 1 hour mark, by taking an overall perspective of what we can understand from our work, whatever we have done till now. As far as the fracture mechanism is concerned, we have noted that the triaxiality is important. High triaxiality, as would prevail near fatigue pre-crack tips under mode 1, would promote brittle failure, and moderate triaxiality, as would be seen in notched specimens in our experiments above 30 micron radius notches. These would lead to switch in the fracture mechanism to ductile void growth and coalescence. And also under mixed mode loading, we see a hybrid mode with evidence of both ductile as well as twin-induced brittle failure having taken place. As far as the role of twinning is concerned, our studies show both detrimental effect as well as benevolent effects. On the detrimental side, we have seen from our single crystal experiments that crack propagates along twin boundaries, and this was also, evidence of this was also seen from the fractographs on the brittle twin-induced fracture morphology, leading to low fracture resistance. The benevolent side, it can cause significant dissipation in the background plastic zone, ubiquitous twinning taking place almost over the entire specimen. And in the ductile fracture regime, as we saw from the unit cell simulations, it can retard the void growth and coalescence. The reason being that it triggers various hardening mechanisms, like the twin-twin intersections, which we saw in our EBST images, twin slip interactions. Twin boundaries act as impediments to dislocation slip, and also texture hardening imparted by lattice rotation. So all this manifests in terms of high hardening and retardation in void growth. Finally, we also note some other effects like severe shearing of voids and coalescence by shear localization instead of internal ligament necking in the fracture process zone, which is also evident from our specimen simulations as well as our unit cell simulations. On the fracture toughness, we found that there's a strong enhancement with the increase in notch root radius, and we were able to explain that through the Rice-Johnson model along with the Rice-Tracy void growth rate equations. And also a significant drop as the mode 2 component increases. In fact, more than what has been reported in aluminum alloys and steels, more than by a factor of 0.5 And we were able to understand this by examining again the microstructure, which plays the most important role as far as magnesium alloys is concerned, shows that again twinning is one of the most important factors affecting both the fracture mechanism as well as the possible dissipation in the background plastic zone. So with that, let me stop my presentation. And I again thank the organizers, the director of IIT Roorkee, the chair of mechanical engineering, Professor Gandhi, Professor Kaushik Pal, and all the colleagues at mechanical engineering IIT Roorkee for inviting me and for patiently putting up with me for the last 1 hour, listening to all my rambling. Thank you very much, and thanks once again. I'll be very happy to answer any questions. I mean, I'll at least try to answer any questions that you may have on this topic. Thank you very much. So let's look at the chart, the chat box to see if there are any questions. So if you have any questions, you can type them in. I'm told in the chat box. So there's one question which I see from Sukrit. So do you think slip mechanism would help absorb energy if used as a front crash beam in a passenger vehicle? Yeah, see, the thing is, slip is always present. And if you look at magnesium, this is a difficult question to answer because as I showed in my slide right at the beginning, the CRSS values for slip corresponding to different slip systems vary very vastly. If you look at magnesium single crystals, the CRSS for basal slip is as low as 0.5. Okay. On the other hand, 0.5 MPa. On the other hand, if you take pyramidal C plus A, it's much higher. So it depends on whether favorable slip like basal slip gets triggered, and you are right in the sense that these soft slip modes, these go in conjunction with twinning. So as I showed you in the optical metallographs, there is evidence of slip taking place inside twins. Okay, so therefore you have a combination of slip and twinning taking place in magnesium. So I think this would together it would contribute to dissipation, but I feel that there is a marked role for dissipation due to twinning in this case. I have one more question here from KS Suresh. So since most of the deformation shows profuse twinning, did you observe the Basinski hardening mechanism within the twinned region? If so, how did you account for such hardening or softening within the twin region in the simulations? It's a very good question. So the Basinski mechanism is the one associated with the sessile to glissile transition. Okay. That can be observed only if you do much more TEM work. Okay, and only that would show us more insights on the nature of the dislocation loops and dislocation mechanisms that would get activated. But I can give you one answer for this, and this is if you look at Surya Kalidandi's work. There's a paper in ACTA in 2010 where they look at different sources of different hardening mechanisms as far as uniaxial compression in magnesium is concerned along the TD or the RD direction. And they examine each of the mechanisms. And they opine that the Basinski mechanism is not so important. They feel the texture hardening and the Hall-Petch mechanisms are more important than the Basinski mechanism. So to answer your question, we didn't get into this in greater detail. And our hardening laws, as I told you in our Fenkelman model, these are phenomenological hardening laws. We have not used dislocation-based hardening laws in our work. And these hardening laws are phenomenological. the parameters have been tuned by benchmarking with experiments. But there are others who have used dislocation models, dislocation-based hardening models. For example, if you look at Irene Berlin's work, she uses a lot of these dislocation models. Again, a lot of very good papers in ACTA and material science and engineering. For example, from Tomei, from Barnett. So these groups have worked with dislocation-based hardening models. We have not done that. We have used mostly phenomenological models. All right. So if there are any further questions, I'd be happy to answer it.
All attendees are requested to kindly post their questions in the chat box.
So let me actually stop sharing my screen. So let me figure out how to do that. Okay, here it is. All right. So I've stopped sharing my screen. So any questions? Yeah, there is one question here. Is the evolution law for twinning similar to standard J2 plasticity? What is the driving force for twinning evolution? Okay, again, a good question. This is from Siladitya. Okay, now there is a lot of debate in the literature whether critical resolve shear stress is again the driving force for twinning. And now, after a lot of work, I think there is a consensus emerging towards CRSS playing an important role. So if you look at some of the eminent researchers in the field, like Barnett and I think recently there is some work from this group, the Spanish group, can't place his name, from IMRE. There's a very recent paper in ACTA, which actually they measure the CRSS for tensile twinning in polycrystalline magnesium around 40 MPa. So now there is a consensus that Schmidt law still applies for twinning, and therefore the driving force for twinning is still based on the resolved shear stress. As far as the phenomenological hardening laws, which we are using in our work, the hardening laws capture the difference between the way in which tension twin develops as compared to contraction twin. In the case of tension twins, as I mentioned very early in my presentation, the twins evolve very rapidly. The width of the twin grows very rapidly, and then they engulf entire grains. So what is done by Zhang and Joshi, who proposed this model, is they use a saturation hardening model. Okay, a saturation hardening model for tension twinning, whereas for contraction twinning, they make use of a Hall patch sort of hardening model, motivated by Hall patch. The reason being that the contraction twins remain narrow, and the twin boundaries act as impediments to dislocation slip. And therefore, you would expect pileup of dislocations at twin boundaries, just like they would do at grain boundaries. So it makes more sense to use that, to use a hardening law based on dislocation slip, based on Hall patch. So that's, I hope that answers your question. There's one more question by Suresh here. Is it possible to speculate or validate the fracture plane using strain localization from the simulations? Again, a good question. I can't answer that fully. This is ongoing work. Okay, and I think your question pertains mainly to the mixed mode experiments, because in the mode 1 case, the crack does grow straight, as you saw in our AZ31 magnesium alloy experiments. So in the mixed mode, the crack grows at an angle, and there's also fracture mechanism getting shifted. We are actually doing some finite element modeling and trying to understand the crack path and how to couple that with appropriate fracture criteria. So we are still not very clear about this. So maybe in a few months' time, we should have a clear understanding of this. Any further questions? So, if not, let me again thank Professor Gandhi and Professor Paul and the Director of IT Roorkee for inviting me to give this talk. Thank you very much.
Thank you very much, sir, for sparing your time and giving a very interesting and informative lecture. And I hope that we will be able to receive you sometime here in IIT Roorkee, and you will not mind to visit us when the pandemic is over. So we will be waiting for your visit so that we can have some more interaction at our department. And now I invite Professor Kaushik Pal to propose a vote of thanks.
So it would be my pleasure to visit IIT Roorkee at the earliest opportunity and interact with colleagues as well as to give possibly another talk. Thank you very much.
Sure, sir. Sure. Very, very, very good.
Okay. So thank you, Professor Gandhi. So it is now my pleasant duty to propose a vote of thanks. So on behalf of the Department of Mechanical and Industrial Engineering, IIT Roorkee, and myself, I express my sincere gratitude to Professor Narasimhan, our invited speaker today, for sparing his valuable time to be with us this evening. So Professor Narasimhan is very well known by his highly recommendable research to this audience. He has distinguished himself in the field of education and scientific research in this country. His contribution to the area of computational solid mechanics, mechanical behavior of materials, and nonlinear and dynamic fracture mechanics is a landmark in the advanced research in the country. So on behalf of the Department of Mechanical and Industrial Engineering, IIT Roorkee, I thank him most heartily. Next, I should like to thank Professor Ajit Kumar Chaturvedi, Director, IIT Roorkee, for his inspiring words and kind support. Also, we are very grateful to him for initiating this activity in the institute. So our sincere thanks and gratitude are to him. I am very much thankful to Professor H.K. Verma and Professor S.P. Nigam, former head of the Department of Mechanical and Industrial Engineering, IIT Roorkee, for sharing their experience with Professor Shankarlal Sharma and enlighten us with his academic vision and administrative capabilities. I am very much thankful to Professor Manoranjan Parida, Deputy Director, IIT Roorkee, for providing us with all best possible logistic support towards organizing this online event. I would also like to thank IIT Roorkee Media Cell for their presence and wide coverage of the event. I am thankful to our head, Institute Computer Center, and his team. Last but not the least, I would like to thank our faculty colleagues and students for all possible care for successful organization of this online event. So once again, thank you all.
Thank you once again. Thank you to all. Thank you.
Okay. Thank you, Professor Narasimha. Thank you, Professor H.K. Verma. I hope that we will receive both of you to campus.
Thank you.
Thank you.
Yeah.
So with this, I think we can close the meeting formally.
Yeah. Yes, sir. Thank you. Bye.
Okay.